All right, welcome back. Today we have text problem 24-17. You all are coming off of WPR, so hopefully you're back in the game, ready to charge into this next portion of the block and preparing yourselves for the term end examination. Well, as we do that, let's go ahead and get out our scratch piece of paper or a blank printout of the problem so we can follow along and tackle this together. All right, so for our read step, as we go through this, we see that we have an arrangement of charged particles. So that should tell us right off the bat that we have an electrostatics problem. Also, we have our overall task for the problem, which we'll write down a little bit later, but it mentions the net electric potential. Well, that's pretty easy, so we have electric potential as well. Notice that it doesn't say electric potential energy, it just says electric potential, and that is abbreviated by the uppercase letter V. Now you might be wondering why the problem statement mentions that the electric potential is equal to 0 at infinity. I'm going to come back to that when we get to the physics step and we start listing out our equations, because the equation itself is going to help visualize what's going on at infinity. Alright, so our draw step is pretty well done for us with the diagram shown. And next we have our given step. Now it lists the charge of our particles here as 5.00 FC. Well, that stands for femtocoulombs. Okay, and that's femto, and that is our abbreviation for times 10 to the negative 15, just like we might use milli or micro or nano or mega or giga or kilo. They all represent prefixes to a certain type of SI unit. Now, femtocoulombs might sound like a pretty small value for a charge, but remember, an electron is still 0.1602 attocoulombs. So that would be times 10 to the negative 18, but since I had a decimal point at the very beginning, it would be 1.602 times 10 to the negative 19. All right, moving along, we have our assumption step coming up next. Now the only assumption we need to make is that there are no additional charges in our system. And we can make that assumption based off of the little nugget I mentioned during the read step, which was the fact that the potential is equal to 0 when our particles are at infinity. That means that when these are an infinite distance away, there is 0 potential at point P. That should tell us that when these four are at infinity, there's no other charges in our system that are acting on the system and would create a potential of anything other than 0. All right, and I'll bring this back up again when we get to the physics step. All right, next up, our task is to calculate the net electric potential at point P, which should lead us directly into our physics step. And first we have to know what the equation is for our electric potential. And since we have point particles here, that means that our equation, our equation is just Coulomb's constant times the charge that is creating the electric potential at point P divided by the distance from that particle to our point of interest, which happens to be point P. To get the net electric potential, then we'll have to add those all up. Now, as promised, we can now go over why the potential is equal to 0 when our particles are at infinity. Now, we have our equation for the electric potential. You'll notice that when our distance from a point to our particle is any value, we divide by that value. But as that distance grows, then 1 over that distance will get much, much smaller until the distance between a point and the charged particle is so great that there's no number for it. It's just infinity. Well, 1 over an incredibly, infinitely large number is going to be 0. So the electric potential of each of our particles is equal to 0 when they are all at infinity. That means when those 4 particles are there, there's nothing else in the system that is contributing to an electric potential at point P. All right, it's time for the solve step. Now, we're probably going to need to number our charges here. So I'm going to go with charge number 1, charge number 2, charge number 3, and 4. And that will help us be able to differentiate all of our particles as we get the net electric potential. So at this time, I want you to pause the video and take your best guess at calculating the net electric potential at point P given the information we've covered so far and how we have our charges organized here. All right, I will see you in a little bit. All right, welcome back. Well, if you had done your reading in the actual textbook, you would have seen an equation that looks a whole lot like this. It doesn't show up on your PRC, but it's the understanding of how electric potentials add up. So if we draw this out and actually complete the sum, because we have a relatively simple system, then it's going to look a lot like this. Now we have 4 particles in our system, and we start with particle 1, and they all share Coulomb's constant in common, so I have that outside. And so it's Coulomb's constant times the quantity of the sum, Q1 over R1 plus Q2 over R2, so on and so forth, until we get to N is equal to 4. Now, one of the major differences with electric potential and electric potential energy is the use of the sign in our charge value. When we were looking at electric fields and the electrostatic force, we put the absolute value of the charge in. That's because we wanted any positive or negative symbol in our result to be because of our vectors, not directly because of the charge itself. But when we talk about electric potentials and electric potential energy, we are going to put in the sign on our charge into the equation. And the reason you can do that is because we want to envision the electric potential as almost like contours on a map. And a positive charge would do something like create a hill or a hilltop. And the electric potential acts as if it were contours on a map. And those contours represent your elevation above sea level. So if 0 electric potential is where we start with nothing there, then envision that as sea level. As we bring a positive charge in, the electric potential at point P raises up above sea level. If you bring a negative charge in, it does the opposite. It brings the altitude at point P below sea level. And the question is, after you've brought in all of these different charges, or the equivalent of geographic features on a map, is the point, or the altitude at point P above or below sea level? So, let's get a visual on what this looks like. Alright, so here's my charge layout. And we look at charge 1 and 2, and they are both positive charges. So I'm going to use a red line to annotate the electric potential of those positive charges. And so at point P, we kind of have this concentric bullseye pattern that goes all the way out to point P. And charge 2 does the same thing. And you can start to see that, hey, this looks a lot like contours on a map for a hilltop. Okay, so we have two positive charges that are creating two hilltops on either side of point P, and that would be the equivalent of a saddle formation on a map, or actually in real life on the ground. But charge 3 is a negative charge, and so it has very similar concentric circles. But because it's negative, we're going to envision this as a depression in or on our map. And so those concentric circles continue out until they get to point P. And charge 4 has the same thing, and those continue out all the way until it gets to point P. All right, so we have two charges, positive, that are creating a raise in elevation, and two charges that are trying to lower the elevation at point P, right here. But however, our equations tell us that the further we get away from the actual charge itself, the less effect it's going to have on our point in space. So charge 4 is further away than charge 1, 2, or 3. And it's like pulling down on a mattress sheet some point far away from where you have a marble of some kind. And the speed at which that marble goes towards the point that you've pulled the mattress sheet down, it's going to accelerate a lot slower. It's going to move slower. It's not as steep. Whereas if you were to pull down on a mattress sheet right next to a marble sitting on the sheet, it's going to go a lot faster. So the effect that charge 4 has on point P is a whole lot less than charge 1, 2, or 3. All right, so let's keep going. We have our equations set up. We have a visual of what all of these charges are doing to the space around these charges at point P. Let's actually do some math. I want you to pause the video. I want you to take the sign of our charges into consideration as we complete our math, and go ahead and complete what we have listed in our equations. And I'll see you in a little bit. All right, welcome back. So the first thing I did is I went through and I simplified the equation that we started with and said that the charge on particle 1 and charge on particle 2 are equal to each other, and they are also equal to the negative of Q3 and Q4. So that represents the positive charges for Q1 and Q2 and the negative charges for Q3 and Q4. Next, I went through and I simplified the distances of each particle to our point in space, point P, and said that R1 is equal to R2 is equal to R3, which is equal to 1/2 of R4, and that's all equal to D. So R1 is equal to D, which represents this length right here. R2 is this length right here, D, and when I get to R4, it is 1/2 the distance, but if I want to calculate R4, then I move the 2 over in front, so it is a distance 2D from our point in space. So with those simplifications, I put that back into our equation, and I represented each of our inputs with their respective colors on our little contour map. And I have V net, I forgot my Coulomb's constant, put that on the end. Coulomb's constant times the quantity of Q over D plus Q over D, those are both positive charges, plus the negative charge given in the problem, 5 femtocoulombs, plus the negative charge given divided by 2D, and that is representing charge 4 with that distance 2D. Now we can simplify this even further by saying right off the bat that these two cancel out because they are equal in magnitude and opposite in sign. All right, that just leaves what we have left, which is the electric potential of particle 1 and particle 4. Now if I want to get a common denominator, which is 2D, then I am left with 2q over 2d minus q over 2d. And now that I have a common denominator, I have 2q minus q. I'm left with just my 1q over 2d Whew, all these colors are exhausting. And all the values that I have listed here in my final equation are known to me because I know Coulomb's constant from my PRC. I know the charge of each of my particles, this one specifically for charge 1, but they're all the same. They're just different distances apart. And I know my distance d. So the last thing I have to do is actually put the values in, and the value I get is 5.62 times 10 to the negative 4 volts. Volts is our SI unit for the electric potential. It's named after Alessandro Giuseppe Antonio Anastasio Volta, who was an Italian physicist, chemist, and pioneer of electricity and power. He was also the inventor of the electric battery, and I read this straight off of Wikipedia, so if you're interested on more of the history behind this individual, then head on over there and you can get your history on. Alright, that's all I have for this time. I'll see you all in class, and if I don't because you are already away for the Thanksgiving holiday, then I hope you have a safe holiday, safe travel, and you come back ready to roll into the rest of our physics semester.